magnetic spectrum. So this is what we're looking at right now is your visible light. That's what our eyes detect. This is what's going to give you sunburn. Then your infrared, thermal IR, that's kind of what we call heat. So start with shortwave. You got UV, visible, and then a little bit into the near IR is what they typically assume to be called shortwave. There's no real formal definition on the wavelengths associated with shortwave, but it's typically that band, and it's usually what's coming from the sun is what they call shortwave radiation. It's kind of solar radiation in general. And then getting into long wave, like I said, it's essentially heat, which is just this range right in here, and that's supposed to extend a little bit farther. But infrared radiation, just terrestrial. This is stuff that's on Earth, things that happen to be the same temperature as we experience here on Earth emit in these wavelengths. So I kind of alluded to this. Objects, if you're a temperature, you emit radiation. The hotter you get, the more radiation you get. So the sun is really hot, it's emitting a lot of radiation, and it tends to peak right in the visible, whereas we're colder, we don't emit quite as much, and then we peak in the long wave radiation or the heat that we're used to feeling. So this is a little fancy graph. Don't worry about the details a whole lot. And this side is essentially energy. So this is what bodies of a certain temperature emit, at least in theory. And so this 5800, that's Kelvin, that's what the sun is emitting. You can see the peak is right in the visible there. And then this is 0, and then there's also a 20-degree C line there, so it's kind of like what we're emitting. You just kind of see the comparison between the energy. So there's a lot of energy that the sun emits. It kind of peaks up here, and we're in here. But with the sun, here's the bands a little bit. So, like I said, long wave is going after terrestrial, short wave is going after solar. That's kind of why we have those two divisions. So this is a lot of stuff on this graph. I just grabbed it off the internet. So this black line on here is kind of what I just had up there. It's kind of in theory, but what happens is when the sun's coming through the atmosphere, it gets filtered out. And you get these different bands where there's nothing really. So this red is basically what hits the Earth as far as energy goes. And so this over here is, again, just considered energy. It's not technically energy, but you can go back to this slide. So all this with respect to the sun, this blue part in the long wave is all filtered out in the atmosphere. So really when you're measuring shortwave radiation, you're pretty much only measuring what's coming from the sun. And when you're measuring long wave radiation, you're typically measuring just what's kind of coming from the Earth. Because this stuff tends to get filtered out in the atmosphere. And that's just down in this region and out beyond the graph. So that's kind of a little physics for you on radiation. So if you hear those terms, you might have a little bit better clue what's going on. So we talked about shortwave radiation and the snow. A lot of these terms you might be familiar with. Albedo. It's just simply, you got what's coming in, that's what I've been talking about. It hits the snow, it flies out. That's your albedo, the ratio between the two. So what percentage is getting reflected? That's your albedo. And for dry, clean snow, 85 to 95% is what is typically assumed. Wet snow, much lower than that. And that's to do with grain size and shape. Because shortwave radiation, snow is white because it scatters, not because it's bouncing back white light. It actually goes in, bounces around, scatters around, and kind of comes back out in all different directions. So that's why it appears white. So these bigger grains, things like that, don't scatter as much, maybe absorb a little more. That's why I get these different values. And then the angle of incidence and actually the angle of observance, I think I don't have that on there. So if the sun's really low in the sky, it kind of hits the snow, maybe it'll skip off a little bit. So the albedo will change depending on where the sun's coming from. And also, it depends on where you're looking. It's a four-dimensional problem. It's really difficult to solve. I think only one or two people have ever solved the whole albedo with all the different angles associated with it for snow. So basically, it depends where you look at it. If you wake up in the morning, there's surface ore. If you get down and look at it like this, it'll look a lot different if you get over top of it. And that's what kind of the albedo change of angle is doing. So, and then wavelength, change of wavelength. So in the visible spectrum, the albedo is pretty high, and that's kind of where these numbers mostly come from. But in the infrared or long wave, the albedo is essentially zero. It's all absorbed. And then also there's something called attenuation. There's a reason why I got this thing kind of faded like that. Is most of your radiation gets absorbed right here on the top, and it kind of disperses as it goes down. And that's maybe 10 to 30 centimeters, depending on what kind of snow you got. Maybe even less than that. And again, that's all depending on grain size, grain shape, if there's dust in the snow, all these different things can affect how the radiation attenuates within the snowpack. So is there any questions? Because this is probably going to be shorter than my allotted time, because I was hoping people would shout out confused. So this is a classic graph from Wisconsin and Warren. This is kind of just showing what the albedo curve looks like with wavelength for dry and melting snow. And so down in this range here is where the visible. You can see it's 80–90%. Here's kind of the near infrared. It's kind of in the middle, and then you get out into the thermal areas, and it goes to zero. It's totally being absorbed. So again, long-wave radiation, this is just being emitted by terrestrial objects. And the short-wave radiation will heat up those objects, and it'll add to this. So, sun hits a rock, it gets warm. Well, that warmth is long-wave radiation. That's what you're feeling. So snow, trees, rocks, all that stuff, us. But snow is a black body, and so in the thermal, in the long-wave range. So just like a black piece of paper in the visible range, in the thermal range, that's what snow is. So it absorbs everything in that range. And so the long-wave radiation hits the snow, it's absorbed right there at the surface. And it also emits very well. So that's kind of why at night with surface or near surface fastness during the day, you get that cold radiation to clear sky. It's because it's emitting these long-wave radiation very efficiently. If you heard the term emissivity, it's because emissivity of snow is usually about 1. That means it's very emissive, which means it's emitting long-wave radiation. That's usually what people are talking about when they mention the word emissivity. And like I said, it's usually just at the surface. So we got a couple examples of kind of how radiation plays. So this is Yellowstone Cloud. That's Lone Peak back there. So this next image is from this little clearing right there. It's just a digital elevation map. And what this is doing is, this is actually, I think, from Mark's thesis, it's a thermal model not a thermal model, environmental model, where the sun comes up and it calculates all the shadows and all the radiation that's going on the slope and throughout the day. And so you can see, and then there's snow laying on top, so you can see the snow heat up as the day progresses. I can find the mouse. So this is a south-facing slope. You can see that these are rocks up here heating up. These are all the trees, and you can see the snow heating up. The brighter colors like reds and greens are warmer. So down here is the shadow from these trees. Now the day's starting to end, things are cooling down. I think that might have been a cloud that came by. So you can just see that the whitening is really warm. I'll play it one more time because the best stuff's probably right in the morning. So really what you can see here is shadows kind of form down here, jammed up. So this is kind of a rib of rocks right here that gets warm. These trees, whatnot, warming up the snow. And there's some shadows down here where it stays cold. So this is kind of the stuff we're working on Montana State. We're mostly applying it towards near surface fastening, surface floor, but there's no reason it couldn't work for where snow's going to be melting first and things like that.
Andrew, I have a question.
Yeah.
With like, you know, that was south-facing slope, and it was March, and I was just curious. You know, you've got this balance between the incoming shortwave and your outgoing long wave. And you know, in Montana, we're fairly far north, and say we have a situation where you're on more of a northeast-facing slope in January or something, and you've got clouds, and then maybe you get a little sun on the slope, and I don't know if you know the answer to this, but you know, the clouds leave, and then, you know, it's during the day, you're getting a little bit of sun on the slope, so you're getting some, you know, kind of oblique incoming solar, but at the same time, you're getting a lot more outgoing long wave because you just lost your clouds.
Right.
And so in a situation like that, are we really heating up the snow surface, do you think? Or do you think you might be cooling the snow surface, or do we not really know until we run some numbers?
You probably don't really know until you run some numbers, but I think generally speaking, especially that time of year, the very surface is probably